Okay, you're welcome to physics lesson for today. My name is Mr. Alagwa Moses, your physics teacher for this session. Welcome to SS2. The first topic for this session will be on scalars and vectors. We'll be looking at what scalars and vectors are, scalar quantities and vector quantities, and how they relate with each other. So first, we'll be looking at scalar quantities. Say these are quantities which have only magnitude or numerical value but no direction. What do we mean by magnitude? It means they have a value but they do not have a direction. These are quantities that have a numerical value but there is no direction in which they are. When you mention scalar quantities, you cannot tell where the scalar quantity is pointed to. Examples of scalar quantities are volume, speed, time, density, distance, temperature. If you look at these quantities that we have mentioned above, I can tell you that the speed of an object is 3 meters per second. You don't know if it is going to the east, to the north, to the south. I can tell you that the distance of a length or the length is 2 meters. You don't know what direction it is going to. So scalars have magnitude, that is numerical value, but no direction. And then vector quantities are quantities that have both magnitude and direction. That means you can tell what side a vector quantity is pointed to, what side a vector quantity is working towards. Examples of vector quantities, just like we had in scalars, are velocity, force, weight, momentum, acceleration. If an object is accelerating, it is accelerating towards a particular direction. If a force is acting on an object, a force we define as a push or pull. If you are pushing an object, you push the object to a particular direction. So vector quantities have direction. The weight of an object acts downwards because of gravity, so it has a direction. So while vector quantities have direction, scalar quantities do not have direction. Vector representation. A vector is represented by a straight line which has an arrowhead, where the length of the line indicates the magnitude and its arrow indicates the direction. When you want to represent vector on paper, you represent it with a straight line with an arrowhead. If, for instance, you are representing 5 meters per second square as an acceleration, the length of the line has to represent 5 meters on scale, and then the direction of that acceleration is where the arrowhead will point to. You can see an example of it here. The length of the arrow or the line tells the magnitude or the numerical value of the vector quantity, while the arrowhead points to the direction. If it is force, a push, like the example I gave, if the magnitude of the force is 5 Newton, the length should be to 5 Newton scale, and then the direction of that force is where the arrowhead will point. Now we'll go to the resultant of a vector. This is a single vector which would have the same effect in magnitude and direction as the original vectors acting together. What we're saying is, if two vectors are acting at a point or acting on an object, the resultant vector is simply the addition of these two vectors. In other words, if you put all these two vectors together, what will they give you? As the diagram above, we have the vector 1 and the vector 2. The resultant, as you can see, is the summation of vector 1 and vector 2. That is where the effect of vector 1 and vector 2 will be seen. The other one, that is the equilibrant, is the opposite of the resultant. It is what balances the resultant. In other words, if vector 1 and 2 are acting on an object, the effect of those two vectors is what we refer to as a resultant. The resultant, which is also the addition of vectors, can be represented in different forms. Firstly, we look at vectors in a straight line. As you can see above, if the vectors are facing the same direction, you add them together. If they are in different opposite directions on a straight line, you subtract them, as you can see above with the examples. So we are looking now at straight line vectors acting on a straight line, and then we look at vectors at 90 degrees. As you can see, 11 kilometers north, to show you that it has direction, is a vector. 11 kilometers east, it has direction. The two forces, when put together, are at 90 degrees, and the vector of those forces is represented with the red line labeled R. And in this case, since it forms a right angle triangle, the addition of these vectors will be according to Pythagoras theorem. And then we have the law of parallelogram of vectors, or parallelogram law of vectors, which states that if two vectors are represented in magnitude and direction by the adjacent side of a parallelogram, then the diagonal of the parallelogram drawn from the point of intersection of the vectors represent the resultant vector in magnitude and direction. That means that when two vectors are acting as the, like for example, we have as the diagram of F2 and F1 are vectors. The resultant of F2 and F1 is the FR, the red line. But now what parallelogram law is saying, if you close up F2 and F1, it will form a parallelogram. The diagonal of this parallelogram, which is FR, can be or is the resultant of the two vectors F2 and F1, and it can be found with the formula below. Then the resolution of vectors. Resolution of vectors is the reverse process of finding two vectors which have the same effect as the resultant vector. Some minutes ago, we were looking for the resultant vector by adding two vectors together. Now, the resolution of vectors is using the resultant vector to get the individual vectors that made up that vector. That means, for instance, if we take a 90 degrees vector, we will look for what we call the component of a vector. The component of a vector is given in a given direction, is its effective value in that direction. So coming back to resolution of vector, the F2 and F1 in the example we gave earlier are the components of the resultant vector. So resolution of vector is simply you using the resultant vector to look for the F2 and F1, which we term as the horizontal component and the vertical component of the resultant. Take for instance the example above. We have the force P, we have the force Q, and then the resultant of force P and Q is R. The resolution of vector is saying that if they give you R, you can use R to look for P and Q individually, and that is R cos theta and R sin theta, where theta is the angle that the resultant makes with the horizontal line. So resolution of vectors is simply looking for the individual component of a vector on the horizontal plane and the vertical plane. By horizontal plane gotten by the resultant cos theta, and the vertical plane gotten by the resultant sin theta. In this case, we're looking at vectors, more than two vectors acting at a point. We have been looking at the cases where two vectors are acting at a point and then we look for the resultant. Here we are looking at more than two vectors acting at a point. The solution for this is that for each vector, we look for the horizontal component, like we just said, where it will now be the resultant cos theta. Theta is the angle that the vector makes with the horizontal axis. And then you look for the vertical component of each vector, which is the resultant sin theta. And then you add all of them up as in the formula above, and then square the horizontal plus the square of the vertical, or square root. Thank you very much for listening. Please do well to attempt the questions in the module work. Thank you.